Hi there, my name is Gabo Zhang. This is my concept topic video presentation for CS529, Fall 2024. My topic is cybersecurity of autonomous vehicles. I've tried to frame the slides with my classmates in mind, but also I think the ideas will be accessible to a general audience as well, with some machine learning awareness and maybe some interest in security. So the paper I started with is this survey paper from 2023 from the IEEE Open Journal of Vehicular Technology by M. Girdhar et al. It's quite a massive survey of over 200 references, and I think they did a great job categorizing things for someone like me approaching from an ML security background. The reason I chose this topic, security of autonomous vehicles, is because I find AVs very concrete and tangible in the real world. And the reason I chose to read a survey paper is because I know next to nothing or knew next to nothing about AVs coming in. So now, to try to make up for this paper being more breadth than depth, I will later on try to do a deep dive into a couple of recent papers cited in the survey, so stay tuned. I did wind up doing quite a bit of reading to make these slides. I tried to cite absolutely everything in that little footnote on the bottom on each of these slides, but anything I didn't cite probably came from this paper, so check it out. So first of all, I wanted to start with the motivation. So why do we even care about autonomous vehicles? We hear about Tesla on the news every single day. Why? And then second, why is cybersecurity a growing concern in autonomous vehicles? Why is there a specific reason that cybersecurity in AVs is such a hot topic? Is there maybe a specific reason that it's inescapably tied to the progress of AVs? Spoiler alert, yes. Next, I wanted to spend a couple minutes just going through vocabulary and core concepts surrounding AVs, because for me, this was an entirely new area, very application focused, a lot of abbreviations. So in order to throw around these abbreviations and combine different research areas in ML with this more consumer-oriented automotive industry, I wanted to just look at the vocabulary a little bit. And then after that, the attack surface. This is where things should start to come together a little bit in terms of terminology, but also what we care about in the realm of vehicles versus machine learning, which is what we're more comfortable with. And then after that, we can approach security. So that brings us to attacks. You'll see most of the attacks are actually what we would call model evasion attacks in adversarial ML, using adversarial examples, which we'll talk about. So here I wanted to deep dive into a recent attack paper, and this is where things should start coming together even more. Maybe some categories and ideas will start to make sense in context. And then lastly, defenses, how you approach defenses, especially in a world where there are adaptive adversaries that can craft evasive attacks in response to your defense. And so here again, we'll look at one of the recent defense papers with some concrete numbers to close it out. Okay, let's dive right in. So why autonomous vehicles? Why is everyone hyped? Especially when we're talking about technology, I always want to go back to the human element. What is this technology if it doesn't matter to a human? So in this case, it's actually very simple. 6 million car accidents a year in the USA, unfathomable injury to humans, many dollars of damage to property. The factors at play are usually speeding, distraction, alcohol, reckless driving, and autonomous driving tech can assist drivers or just be in full automation, can eliminate every single one of those factors. So now, why is cybersecurity of AVs so popular right now? Well, it's again simple because machine learning and AI are so popular right now. For the past decade, ML has made insane progress unlocking complex data-driven tasks. Driving, if you think about it, is all about data. We navigate unique scenarios like construction sites, etc. by encountering them. And most cutting-edge driver assistance tech nowadays uses some kind of ML, and many of them even now use deep learning, so ML architectures with many hidden layers capable of emulating really complex patterns. So throughout the 2010s, vehicles have been adding smart tasks, but something else that has been happening since at least 2014 simultaneously is that people have figured out ways to mess with ML algorithms as well to get them to mess up. So the reason I mentioned 2014, if you take a look at the timeline on the right on this slide, you'll see that there's kind of a split in terms of traditional ML adversarial attacks into this new realm of deep neural networks, DNNs. So for these modern neural nets, they're able to achieve so much more with all these hidden layers by emulating human neural networks. This opens up a whole new world of sort of black box exploits that you can have. So kind of an explosion of ways to attack these complicated networks that now are applied to so many things. Simultaneously on the left, I want to tie this to autonomous vehicles. And so you can see that in the 2010s, a lot of tech and machine learning goes into cars all of a sudden. It's just progressing ML all across the board. So as a result, vehicles are becoming ripe for adversarial ML attacks. It is the place where you see a lot of applied ML, because where else are you seeing ML algorithms, vision tasks so concretely used in real life? In reality, not a ton of targeted attacks have been reported. You don't hear about Tesla Autopilot getting tricked in the news, but there is huge latent potential there because the threats to AVs can be intentional or not. AVs take in their environment, so AVs make mistakes naturally from misinterpreting the environment. But humans do have ways of intentionally boosting that misinterpretation, and that's what we're going to talk about today. And just to refer back to the human element, what does a consequence of this AV misinterpretation look like? Well, we really care because it can look like a car running under a semi-truck or hitting a person. Something to think about there is just there is a potential legal gray area. Who is responsible when a fully autonomous vehicle, which by the way currently doesn't exist, if it crashes, who's responsible, driver or the manufacturer, right? It depends on if the manufacturer made guarantees and a glitch happened, then it's not the driver's fault. But it really depends on what is promised. Now, I wanted to spend a minute here to put this slide up for reference on common vocabulary. What I found is that AV security papers are very applied tech focused, which means they throw around common abbreviations like crazy. So let's just familiarize ourselves here. Autonomous vehicles, AVs, let's define it. Vehicle with ability to move or take action without the aid of a driver. Very general, or sort of high level thing. Autonomous driving, AD, same thing. Automated driving system, ADS. Now, that just refers to a car with a certain level of automation. It's the preferred term here as opposed to self-driving cars and all these like fully automated systems, etc., because those things get used a lot in marketing, promising things that aren't fully here yet by like a strict standards type definition. Like Tesla has their FSD, fully self-driving vehicles, right? But it's a little bit misleading. It's a great marketing term, but we want to be more precise in literature. So an AV's ADS can perform steering. That's a big thing. And then the other thing is acceleration or deceleration. So just two things there to keep in mind. And then in addition, can intelligently monitor roadway conditions. We're talking about traffic signs, lane markings, pedestrians, and SVs, surrounding vehicles. And now ADAS is actually very different from ADS. It refers to vehicle tech to assist drivers. Think of it as a stepping stone towards fully autonomous, like the highest level of ADS. Now, the examples here are probably more obvious to us. Adaptive cruise control. So you're in a car, you have cruise control on, you're going 60, the person in front of you slows down. You don't want your car to continue going 60. You want it to also slow down if the person in front of you has suddenly decelerated. So that's an automated, like a very simple task that is a stepping stone task, again, towards eventually getting to that fully automated level. We also have TSR, very commonly examined in literature. You got lane keeping, LKA, and then forward collision warning, FCW, etc. And just to give you an idea of ADAS research, here's a list from that survey paper of state-of-the-art ADAS tasks and solutions. So a lot of papers. Thing I wanted to point out here is it's interesting to me that every type of ML at this point can still achieve state-of-the-art. Like we still have SVMs in 2022. We have CNNs, ANNs, of course, but like using k-nearest neighbors, we still have papers in 2022. Random forest, decision tree, etc. Now I want to go deeper on AVs. So how to think about automation, levels of automation, because again, more automation, more ML, and that's what we really care about from here on out, right? And it's only going to be more ML from here on out. So what are we looking for? ODD, that's the conditions you can operate in. That's the first sort of criteria we're going to look at. So operational design domains, some common parameters there, non-movable, movable, and environmental conditions. So we're talking scenery, like that's the roads, that's the traffic lights. We have weather in the environmental conditions, and then dynamic elements, the movable things like the vehicle itself, and then also surrounding vehicles, the traffic, etc. So now how do we classify by ODD? What are the levels, right? And so we look at perception. So that's how much can vehicle sensors perceive around itself? How much can it mimic what a human can do? And then the second category is connectivity. So how much, this is something humans can do, but how much communication can the vehicle access? So we have vocabulary like V2V, vehicle to vehicle, V2X, which is X is everything else. It can be IGP, infrastructure, like a power grid, pedestrian, etc. And then we also have the connectivity of in-vehicle communications. So that can be Ethernet. And then I wanted to point out CAN, controller area network, which is like network communication but internally between the vehicle's ECUs. And ECU, I feel like, is another important piece of vocabulary. Electronic control unit. So one of the car's many, I've seen numbers around 150 computers inside the car. So they're modules controlling an electrical system. And the biggest one that people talk about is the ECM, engine control module. But like ABS, you've probably heard of that from the stickers on your car. But anti-lock braking system, the infotainment system has an ECU controlling it, etc. The second consideration for levels of automation is something called DDT, so the dynamic driving task. And that's very simple. It's just the lateral and the longitudinal motion control of the vehicle. So when we say lateral, we just mean steering, like, left and right direction. And then longitudinal, we mean the speed, the acceleration, deceleration, speed control. So perspectives for classification, like earlier, it was, perception and connectivity. Here, it's going to be the extent, very simple. So just do you have lateral or longitudinal or both? And then there's a fallback, right? When automation fails, does the human step in or no? And the thing right now is it's always going to be yes. Up until this point in time on public roads, I mean, humans are always supposed to step in for the vehicle when the basic tasks, whether it's an assist or like a full automation system, fails. So below there are some images there. I tried to sort of point out like how well can you perceive and connect for the ODDs. So there's a slick little image there, and then DDT is just like the movement, the motion control. So here's the actual graphic from the paper, which I think clarifies some things in context, but also if you look across from left to right, from level 0 automation to level 5 full automation, it's not too much difference, right? Each of the marginal differences is like slightly better than the previous one. But you can see here perception, connectivity, we have ODD sort of level, DDT level, and then the DDT fallback pointed out as well. So this is the SAE J3016 standard. This is Society of Automotive Engineers. It's kind of an aspirational standard because, and I wanted to highlight this. Now, you know about Tesla's autopilot. It's been around since about 2015. That was on the earlier graphic. It's very advanced at this point, has that FSD mode, the fully self-driving, marketing term mode. It's classified here as, let me get the pen out here, level 2. Which actually was very surprising to me. So this is a very aspirational type classification for general driving. Nowadays, like Tesla definitely has sensors that can cover all around the car, like better perception than a human. But there are some limits, right? The fallbacks are always going to be a human, and you have to achieve certain standards to attain these levels. Now, for a concrete example of potentially something in the higher levels, you can picture a driverless bus maybe doing one very specific route on a campus, picking up people, dropping off people, but it only runs one route. It only needed to train on one route. And with that, you can actually achieve these higher levels because there can be no human fallback. It can be all automated. But the reason that Tesla is stuck at level 2 is that it is trying to do it for every road in the entire world. Okay, so that's enough high-level background on AVs. Let's start moving towards machine learning, towards ML, and then towards security. So for machine learning, the first thing we care about is inputs and outputs, right? So for a vehicle as a model, this is surprisingly straightforward. We have sensor data and connectivity data, like we mentioned previously. Perception data is the input to the car for making decisions. So output is literally drive the car, right? Earlier we talked about steering and speed control. In other words, the actuator actions, the actual hardware that's affecting steering and speed. But I wanted to formalize that a little bit more with abstraction layers, as mentioned in the survey paper. So think of the AV itself as a machine learning pipeline. What are the abstractions that we can make in it? So here is the chart. Viewing an AV as an ML pipeline, we have 4 phases, abstractions that we can address. So we got inputs. Those sensor data is over here, and then think of the actuator movement over here. But in the middle, we have a perception phase. We're talking about sensors and the basic results of the sensors. So I checked a couple of sources. I think this is wrong here. I think object detection needs to be over here. But that's generally what we're talking about. We're talking about segmentation of images and then also the classification of those images. These all belong in this group of thinking. And then we can talk about predictions as the next part of the pipeline. And this is, we're talking trajectory. The car to my right is trying to merge into my lane. Blinker is on, and it's currently like it's veering over. He'll be fully in 5 seconds, like that kind of trajectory. But then in the same category, there's also higher level trajectory, right? Higher level prediction. So maybe of where traffic is going to be congested in 30 minutes. So that's also a type of prediction. The same sort of machine learning deep nets can approach both of these type of problems. There's like a smaller scale and then a higher level, right? So this is even more famously exemplified in the next category, the next abstraction of planning. So in planning, famously, there is local planning and global planning. Local is whether you do the next stop or turn given a pedestrian is there. So how do you navigate that pedestrian? And then global planning is, again, higher level version. So what is the route you want to do? Maybe run a Dijkstra's algorithm on nodes to find the shortest path to your destination, given the constraints. And then finally, we have basically touching the hardware layer. We have decision making and control. So we're talking interaction with the ECUs. We're talking tweaking the steering and speed to avoid a collision avoidance. Now, you'll notice that an ADAS task, or remember that assisted driving task, will relate to basically every part of the pipeline. So TSR is a popular one here. And in the perception phase, for example, it would be in relation to this task perceiving the stop sign through camera images. So image semantic segmentation and then classification subsequently. In the prediction phase, what does this have to do with prediction? Well, you would predict that the current vehicle that has interpreted a stop sign is going to slow down and stop. You can also predict surrounding vehicles, what they're going to do. You're going to know that they're going to want to stop as well. So planning, how does this play into planning? For local planning, of course, you plan to stop at the stop sign. That can be figured in. And then I tried to think of a global planning example here. So maybe when you stop, you can then make a turn easily to avoid potential congestion. It's the higher level thinking again. And then in the final decision making and control phase, for a stop sign, you maybe maintain steering and decelerate. Now, you're probably thinking, wow, we just spent so much time on AV fun facts. Why? Because I wanted to make sure it's fresh in our minds which parts of AVs use machine learning and thus are accessible as an ML adversarial attack surface. So what can an adversary actually target? So here I wanted to make a note that in our class, CS529, we've had the privilege of actually studying ML systems attacks pretty extensively, the categories and such. So to both my excitement and dismay, it seems like when discussing security of AVs, the discussion is kind of a subset of what we've already covered in class. So it's cool to see it applied, but I will end up rehashing some of the concepts for the benefit of the general viewer. So let's jump in. There are a handful of different categories of ML attacks, but one is really, really common in AV literature. Why is that? Well, when we try to target the ML pipeline of an autonomous vehicle, there are some things we can't easily mess with, or maybe it's the other way around. Some things are just too easy to mess with, so we always mess with them. So driving data is easy to collect. It's going to be pretty impossible for you to get Tesla to use your poisoned, manipulated data set for training their models to attack it that way. So that kind of rules out things like planning triggers for backdoor attacks, because you just can't get to the data of a lot of these proprietary companies. So we're usually looking at attacking at inference time by sending specific inputs crafted to trick the model. So what about access to the model? Well, cars are made by big companies for profit, so chances are not great that Tesla is going to open source their cars. So we're usually dealing with a black box here. We're going to have to deduce what's going on behind the scenes in terms of model architecture and also model parameters and approximate it ourselves using a model that we do know, that we kind of train ourselves to act like the black box that we're trying to clone. So it all boils down to creating adversarial examples, aka crafted malicious inputs, to trick cars into doing the wrong thing. This is by far the approach that makes the most sense, and the rest of these slides will be talking about adversarial examples. This is also called model evasion, and one thing that I did want to mention here is that adversarial examples, you ideally want to involve minimal perturbations on real inputs. What I mean by that is you want it to look like it's real, like humans wouldn't be able to tell. Because if humans would be able to tell, then it's not really an attack specific to autonomous vehicles then. All right, so now we're going to get into a little bit more technical stuff. So how do you generate an adversarial example? Well, the intuition comes from gradient descent, right? So usually it's used for training weights towards minimizing the loss function, right? So that's how you train models is, you go through the forward pass, and then there's a backward pass where you do back propagation with the chain rule, and you get the gradients to be able to calculate this right here, which is DLDW, right? The gradients of the loss function, which kind of you'll see inside here. I've put y hat and also y. Y is the correct thing that you want to output. You want your model to output. Y hat is all the math, all the layers inside the model that try to get you there. So I tried to parameterize this loss function with the appropriate things. I wanted to illustrate that loss depends on the inputs, the x, and also the weights of the model, sometimes called theta. So DLDW, again, is the gradient of the loss with respect to weights, and we use it to step the weights towards weights that result in smaller loss. And so there are better weights in the end for what you want the model to do. Now, the hack here, which is like, how do you use this to generate adversarial examples, is to use the same logic as gradient descent, but instead you train the inputs towards maximizing the loss function. So let me clear that out first. So you get the gradient with respect to the inputs instead of the weights. So with respect to x instead of w. Notice how the model's y hat it's still parameterized by weights. So you're assuming that you have the weights. It does require white box access to this trained model, and then you keep it constant there, and then you do stuff to the x. So notice that it's DLDX here instead of DLDW. And then the second part is to use this to step the inputs, again the x, towards inputs that result in a bigger loss. So the orange here, see that we changed that minus to a plus. Basically what that looks like is you want to minimize the loss generally. That's the good thing. You have a gradient here that's pointing in that direction, and you want to go the opposite direction. The gradient is pointing towards the top of the loss mountain. You want to always descend towards the valley of the loss mountain where there's less loss. By definition, that's your objective. And so you want to go negative. You want to go away from this gradient. And then in this case, though, instead of wanting the objective to be down here, you want the objective to be down up here, because you want the model to perform badly and maybe classify an entirely wrong answer. So the gradient still looks like this, but now you want to go with the gradient. So you want to add the direction of the gradient to your current x. So if your x is here, you want to move this direction, right, to get to here. Now there is another way actually to generate adversarial examples that don't involve using that little trick with the gradients, and that's to use a GAN. The previous gradient descent kind of method is from around 2014, and here we're talking about something that's more popular since 2018. So using a GAN is a generative model that uses a generator and a discriminator, and they have opposing goals. They fight against each other, and then they both sort of get better, where the generator is the thing that you really care about getting better. So convergence, theoretically, when it's done correctly, everything plays out correctly, sees the generator making examples that are good enough to confuse the discriminator. And the loss function in the original 2014 GAN paper is pretty famous, but here is a kind of a restatement of it in this 2018 ADV GAN paper. And the hack here is to choose GAN's loss function. You make a machine learning model work for you by configuring its loss function, its guiding objective, in a clever way. This looks like a lot of math, but it's just saying simultaneously, let's move towards 1, making example inputs that trick the target model, 2, making example inputs look valid, and 3, making the perturbation small. This is similar to 2, but it's more restrictive, right? It has to be based on a real thing. Okay, so now we have an adversarial example in hand from using one of those two methods, either gradients or GAN. That's cool, but what if I told you that the same example can now be used successfully on a bunch of models? So it can actually be a whole lot more powerful than you might expect because of something called transferability. So this is an easy extension of adversarial examples. So this is from a paper in 2016, cited below. If you generate these adversarial examples on a white box model that is approximating a proprietary, hidden, obscured black box model, then this adversarial example may be effective on that black box model as well. The implication here is huge because take your own model that you know everything about. If you can get it to do the same inputs and outputs as the black box model that a company is trying to protect, and then you can make an adversarial example on your own model, then this same example may directly be usable on that protected proprietary industrial model that is under protection. So how is that useful? Well, now there's a two-step approach to attacking a black box. So the first thing is you try to turn that black box into your own white box. You clone it with your own model, and then you run that gradient descent or GAN trick to generate AEs, and then you hope it transfers. So a problem in that first part, though, is a query limit. If you can't quite treat that black box model as an oracle and heavily query it to get a ton of input-output pairs for training data for your own model, then that might be a problem. And then in that second step, a problem may be that the gradients may not transfer. Failure is still possible here. Now we're getting to the specifics. I just want y'all to keep this categorical information in mind while we talk about specific attacks. So as you can imagine, most attacks relating to machine learning target the very first category here, which is adversarial examples hitting these sensors in charge of perception. A sensor example is LiDAR. So LiDAR shoots out a laser and uses the reflection to gauge how far something is. So if you shoot back a similar laser, that messes with how far the AV thinks an obstacle is. A spoofing attack example on the right there in that little graphic, if you can trick a car into perceiving a pedestrian when there is none, you can get an AV to suddenly brake. This can cause an accident, a rear end from the person behind them, and a subsequent pileup, all because of one misperception. Now finally, we can dig into this paper. So the paper is called Public Attention-Based Adversarial Attack on Traffic Sign Recognition, TSR. This is from 2023, so just released, and it's an attack on the TSR task that we mentioned earlier in respect to ADAS, the Assisted Task Systems. So this is at its core a computer vision classification task, and we're talking about earlier we mentioned sensor spoofing, and then it's also an evasion attack in the sense that it constructs an adversarial example. And so here the method is, like we mentioned, transferring a white box adversarial example to test on black box models. In this case, the models are known, but they hold them as black boxes so that you have to then approximate them with white boxes. The novelty here, just as kind of a spoiler, it's a technique for better transferability using multiple white box models. The point here is we're really starting to stitch together all these concepts we've introduced earlier. Every single one gets used here at the cutting edge. With a lot of these attack papers, the setup is similar, all to showcase a clever novel technique at its core. The one here is public attention. So the intuition behind this technique is humans efficiently allocate attention when we're looking at a scene. So computer vision does the same thing, right? There's attention in machine learning. So we can visualize attention, what the model is looking at, using something called an attention heat map, so AHM. So to improve adversarial example transferability, this paper wants to target generic features that are commonly paid attention to in multiple models when trained on a certain task. So it finds commonality very simply by averaging a bunch of model heat maps. But what an attention heat map looks like is shown in the figure on the right. So just imagine, like 3 of these, all with, the red attention, like high attention section, a little bit differently distributed, but you average them together by this equation and you get the public AHM, the PAHM. You want to aim your perturbations at these little areas on average highlighted in red. And here's the loss function to do all that. H here is that public attention heat map. As always in ML, you want to use the loss function to guide the model towards what you want. What the authors here want is to make the model fight its own classification. And so specifically it does this by bringing the 2 attention heat maps, the one leading to the correct classification and the one leading to this incorrect second option. You want those heat maps to be constrained to be close together. The smaller this value is, the more the authors achieve their adversarial goal. This works well, so check out the visual on the bottom. Row A is the original dataset image. Row B has 2 models averaging their heat maps. Row 3 has 3 models averaging their heat maps. The paper finds that more models is better, which is maybe what you would expect based on the intuition, and it's nice that they find that. Notice, as always, that the AE perturbations are something not substantial to humans. And finally, just looking at the results, we're focused on multiple models coming together. We'll see that the results here at the very right have much higher percentages, error rates, so successful attacking. And then we'll also see that, with more models, that's the higher error rate, aka the attack success rate up here. So now what about defenses? Generally, there are a couple ways to think about defenses. So one is to categorize it as either proactive defense or reactive defense. So what those mean is proactive would be something like adversarial retraining, where you incorporate AEs into your training set. So how do you get those AEs? Well, you can use the gradient descent technique or the GAN technique yourself. On your own training set, you generate these things and then add them to the training set, augment the training set. Feature masking is another example where you make the model only look at crucial parts of an input. Think of a person's face. You don't want attackers hiding perturbations in the pixels of the background sky. So you can mask that away. Gradient regularization is where you modify and use the loss function to penalize the size of the gradient with respect to the input, that DLDX that we were talking about earlier. So that makes the gradient method for generating AEs way less effective, way slower. So a problem here for all these proactive defenses is it's a trade-off of model accuracy for robustness, right? You're killing your model a little bit when you do these things. And it depends on your threat model. How much do you feel, how threatened do you feel that you're going to be attacked? Think about who wants to attack you, their capabilities, their goals. Now, reactive defenses is like, you don't want to touch your trained model. You don't want to modify your training, but you do want something in addition to detect those adversarial examples. So that is what adversarial detection is. Input reconstruction is cleaning the input to be more like it, quote, quote, it should be. So how do we know what it should be? Well, you have a lot of data and many techniques to find patterns and averages, right? And we're going to get into that a little bit more. Network verification I wanted to touch on. It's a formal method, so it's like a guarantee mathematically that a small enough perturbation, like an epsilon, should produce the same classification. So this is a bit more expensive and may not scale so well, but it is more of a formal mathematical guarantee. So this paper is called Towards Autonomous Driving Model Resistant to Adversarial Attack, also from 2023. Now, here's the setup of the paper. It's a reactive defense doing input reconstruction. The auxiliary model that I mentioned is a generative autoencoder. So I'll explain that in the following slides. The novelty at the core, though, because generative autoencoders are often used for input reconstruction, is this memory module, quote, quote, that they keep track of. They use to keep track of what features should be. Now I want to mention here that remember the GD and like gradient descent and GAN methods for generating adversarial examples? Well, here are the papers they're tied to. FGSM is the technique, original technique for gradient adversarial examples, and then ADV GAN from 2018 is the GAN one. And so they're referenced here in this paper, and these are the two attacks that they test on. So, I mean, these are from 2014 and 2018. It's these methods at their core are still relevant in 2024. Now, briefly, an autoencoder looks something like this. So it's an encoder-decoder pattern. So the idea is two models. One to compress the input into this hidden representation space, and then the other to decompress / reconstruct from that blank space, or from that space back out to ideally the same thing as the input. Now, why on earth would you want a model to, give back something that looks like what you put in? Well, because you want the model to know how to generate variations on things, but then why do you want that little hidden representation space pocket? Well, because you might want to design some manual inputs to feed into there. Now, let me explain. VAEs, variational autoencoders, are kind of a more concrete example implementation of that design pattern. So the points in that linked moon scatter plot on the left, so that's X's and Y's visualized in 2 dimensions. You can think of that as 2 features, 2 dimensions, right? So we can use some deep learning architectures. So I've done this in the past with some fully connected layers right here to transition from the 2 dimensions here to more. And then eventually, in this case, you want to distill that down into, that is again, 2 dimensions. You're going to ascribe meaning to these 2 dimensions used in this hidden representation space. The 2 numbers are going to represent mean and standard deviation of a normal distribution. You can use a normal distribution sampling function and then use these numbers that this encoder has outputted, and you can generate this z vector. So this z in this example, you can think of it as generated random distribution noise. Now you can feed it to this decoder here. Now during training, this decoder is going to get really good at turning a sample from a normal distribution, the z, into something that looks like the linked moon's data points. Once you're done training, And here's the application of all this stuff. You lop off the encoder, and then you start right here, right? You start with the Z, and then you just use the decoder. You use your own normal distribution sampling function and a random number generator, and you can make your own random Zs. You can feed this random noise into the decoder, and you're going to be generating new things that look like that original moon's shape. Now, after that detour, back to the paper. So this is the architecture on the left here. You'll see they have some design cues from GAN, a discriminator to, again, fight against the rest of the model, pushing the rest of the model to generate things it can't obviously tell are adversarial inputs. You'll also recognize the autoencoder pattern from the previous slides, but the key here is that what they do in the Z part, in that hidden representation space, that's the interesting part. So think about what we talked about in the previous slide with making that space useful and meaningful. Here they have this memory module. And the memory module is just a matrix. It's a collection of vectors that represent what is considered normal. So when reconstructing, the encoder's output is actually just weights. They are like coefficients used to do a linear transformation using the vectors collected in this memory module. The Z that you get out is this combination from a finite set of vectors contained in this memory. In other words, the reconstruction is limited and it performs kind of a regularization of the natural input to the model. It cleans it. With that intuition, let's get back to the real world. Here are some real world effects of adversarial examples as measured in the paper. So we have hijacking, which has to do with steering. So the steering angle deviation of like 0.3. Vanishing, no objects detected. That's the one over here. Fabrication, that is an absurd number of objects being detected. That's the one right here. And then mislabeling, that's the one here. Cars are labeled as pedestrians. White box here means that researchers had full knowledge of the driving model and could use it to create adversarial examples. Black box, again, means researchers had to jump through their additional hoop of doing that model extraction attack to make their own white box version of the black box model. So it's less precise, and obviously the black box attacks, as you can see in the table, are slightly less effective all else equal. So that is attack success rate before this paper does anything. So you'll notice two things here. One is the white box attack success is higher, which makes sense. And two, ADV GANs success rate is higher across all types of attack versus FGSM. And here, finally, some results. On the left is a cleaned image example, cleaned via the autoencoder and memory module vectors reconstruction technique. So important to remember that all this is happening on images, and we can't see any of it. Remember that previous slide where the model was going crazy with all those labels? Well, that's an adversarial example, but we can't really as humans tell. That picture kind of looks like the other three. On the right, you can see that the defense success rate is quite high in the bold. They actually additionally compare to other defensive mechanisms like the ones that we gave examples of earlier. Now, to wrap up, I want to go back to my point about how big and obscure the AV pipeline is. Remember the 4 phases of the pipeline? So it's easy to think about adversarial examples targeting the perception part of the pipeline, but the other parts of this black box can have hidden issues as well. So fuzzing is an automated way of discovering bugs and vulnerabilities by feeding in random input into a system. So this is a more realistic, maybe, way of exploring this big obscure pipeline for unexpected exploits. Now, this example that just played, this example is of an adversarial driving maneuver that exploits the planning phase. And the authors from Purdue find these exploits via fuzzing. Now you might notice in the video there, that black Cybertruck looking car, it kind of drives normally. This is not a perception attack. The car is not really perturbed in how it's driving, but this exploits something in the machine learning abilities of the planning model, which doesn't expect exactly how that car was driving. And this is something that you can find via just mechanically trying a lot of inputs. So that's it for this presentation. Thank you so much for listening. To just sum up, very few adversarial ML attacks have been reported in real life, but the pipeline itself has a lot of black box operation and a lot of potential to be exploited. The main focus for today was adversarial examples, aka evasion attacks. Modern attacks and defenses revolve around how to strengthen AEs or how to weaken them. Now, adversarial attacks mostly are on image classification. AEs do generalize to audio, etc., but in the field of adversarial ML, most work is on classification models. So one thing I did want to mention is that autonomous driving models At the very end of the day, when they move those actuators, they are regression models. So defenses may not be transferable in that sense. And finally, to leave off, defenses must be considered through the lens of Kirchhoff's principle. No security through obscurity. That's something that we should always be thinking about. Thanks so much for listening. Please have a nice day.